So now we have established the model G as a fractional order transfer function. So the next topic is how can we analyze a fractional or linear fractional order systems. And in this part, I will talk about Leffler function first, with application, and also how to calculate it. How to calculate it with the use of Matlab functions. And then I will talk about analytical solution of commensurate order system. That means the order of the systems are given like something like this: Sn alpha plus Sn minus 1 alpha, which is a special case of conventional fractional order transfer functions. So we call it this one commensurate order system. And there are limitations in this part. So the method presented here is only for commensurate order systems. We can analyze the time response and step response and impulse response of the system. We can get analytical solutions to the problems. And then I will extend the idea by the use of Grunwald and Zheleznikov definition and find the closed form solution to ordinary fractional order transfer functions. It is not necessarily being given in commensurate order, so it can be any fractional order transfer functions. And then I will present the analysis such as stability, frequency domain analysis, and time domain analysis by the use of fractional order transfer function objects. So now let's consider a Leffler function. I think Professor Lee has already talked about a Leffler function already in detail, and these are the definitions of Leffler functions in one parameter. And these are the special examples for that kind of functions. And also we have the function in two parameters, alpha and beta, which are essential in finding the analytical solution of the system. And also, in some cases, we need the integer order derivative of the function in the analytical solutions. So, since I summarized this part, I think we'd better create a function called ML function, and I'll write this function myself. In this function, we can specify alpha and beta for the two-parameter Leffler function. For one Leffler function, we just assign beta to 1. It should be okay. And this is the signal of y, and this is the derivative, also the derivative. And the function itself is very simple, and it can be executed very fast, much faster than the use of MLF function by, I think, called Lubny. However, there are limitations here. So, since I only used the finite term summation of the approximation to the original function, when the value of x is very large, then this function may lead to infinite terms, infinite numbers. So I use the trick here. In this function call, if we can find a convergence f, then we can accept the result. If f we obtain is not convergent, it tends to be infinity, then we can call the Pavlovni's function. However, in that function, we cannot use n there. N must be 0 in that function. So now I've embedded that function in my code. and this is my function. And if the result is not finite and n is 0, then I will call the function like limit. It could be rather slow, but it is accurate enough for most applications, I think. And here are examples. I think you can try the examples yourself. And now let's consider analytical solutions to linear fractional order differential equations. And the standard form is given like this. However, this is a simplified version of the general linear differential equations, because the right-hand side is given as a step function only. So for this system, if we try to solve the fractional order differential equation, we come with a very complicated formula like this. And I don't think there is any existing Matlab code for solving general solutions of the system for step responses. And there are limitations also, because it can only be used to solve step response of the system, and also the right-hand side must be a step function. You cannot replace it with any other functions. So this formula is quite complicated. I didn't do anything to this function because it's too complicated. So normally in control literatures we will see that they will analyze the step response with a 3-term system like this, and the analytical solution to the step response of the system is simpler. However, it involves infinite time. And for this particular system, I read this code to solve the problem. And there are quite a lot of limitations in the code, because we can only deal with 3-term systems, and we can only deal with step response of the system. Numerator must be a constant. So there are quite a lot of limitations, and I'll talk about it too much. So this is the Matlab code. If you want to try it, you can execute this function and see what it gives. And since the original solution has an analytical form, so for a particular system like this, we can easily find the analytical form of the solution. However, the solution is based on the, I think there is the extra s there. Let's remove that part, extra s. So we can write out the analytical solution, but the actual analytical solution is quite complicated, because there is an infinite summation to the terms. So normally we should not use this kind of expression as analytical solutions.